கேட்கலன்னா அவ்வளவுதான் வராது.
டிஃபியூஷன் பண்ணேன். இதே பண்ணு.
இல்ல நான்
Good morning, one and all. It's my great pleasure to invite our chief guest, Dr. E. Selvarajan, Assistant Professor, Department of Genetic Engineering, SRM Institute of Science and Technology. He has completed his PhD in VIT. He is a Senior Research Fellow of DBT, Indo-Russia Joint Project, and ICMR. He is a trainee in Biosync BCIL. He has filed 2 international patents. He has also published 9 books and 74 paper publications in reputed journals. It is remarkable that he has 7 professional membership and also a reviewer and editorial board member of various journals. He has received Young Scientist Award and Best Environment Research Award. Sir, please.
Yeah, thank you for this wonderful introduction. Today we are going to see a topic called like nano-immobilized biocatalyst and their potential biotechnological applications in bioenergy production. So uh, today I have just planned the presentation into two basic divisions. Like the first part will be like very basics of what is called nano immobilized biocatalyst, and the second part will be like what we have done in our lab, and what are the publications we have done so far with respect to this nano immobilized biocatalyst. So for this, uh, just I'm thanking Dr. Praveen Kumar, HOD from Arun Engineering College, and Dr. Selvaraj for this wonderful opportunity for this FDP talk. So we all know that the sustainable development. So this is the hot topic we are actually seeing for the past 2 years, and where this UN actually set up 17 goals actually. So we have starting from like no poverty, like zero hunger, all these things. So and we are mainly concerning the next 45 minutes we are going to see on this affordable and clean energy that is in the Sustainable Development Goal number 7 actually. So we are going to see on this topic alone for the next 45 minutes. So you should know what is, first of all, like there are many research going on in the area of like sustainable development. So we should know what is called sustainable development. Okay, and mainly like the last decades or last 20 years, we are all working towards this social and economical background. Like no, we are only concerning only on this economic part as well as the social part. But most of them have forgotten about this environmental. Like so we have to protect the environment, and we have to see what are the things which is there. So we have also introduced this environmental thing, and altogether we have to see both social, economic as well as the environment. So that is the combined part of all these things. So that is called as a sustainable development. So as the economic should also go like the social as well as the environmental concept. So all this combinedly we call it as a sustainable development. So when we see the sustainable development, that is the actual goal of this one. So we should actually see the what is this? The planet, the people, the prosperity, the peace, the partnership, everything into account. So mainly the planet, like no, the Earth, which we are actually living here. So where we have to protect the planet. Okay, so where we have lot of climatic changes happening. So we are also encountering this climatic change happening even in Tamil Nadu also. So this actually plays a very important thing in the coming years also. So how to this sustainable development can be enhanced in the future generation. So down the line of 2047, as our Prime Minister also have a focus on the goal. So we have to go move around how this we can able to do it. So that is what we are going to see in this the next 30-35 minutes. Okay. So the topic is, if you see, we are going to see what is called nano immobilization, first of all. all. So this topic is actually a very, if you see, immobilization is actually a very long 20 to 30 years itself. We are using this immobilization strategies, but now we have a concept called as like nano immobilization, because nano also playing an important role in this one. So when we combine this immobilization as well as this nano part here, so we have a very strong technology called as a nano immobilization. So that is what we are going to see here. So, uh, first of all, we have to see why we are going for a immobilized enzyme or like immobilized biocatalyst here. Okay, so when the normal enzyme, so when the normal enzyme we have it in our lab, so which can able to degrade, or which can able to we cannot lose the enzyme because the enzyme itself is a costly one. So that is the reason we are going with a immobilization or immobilized biocatalyst. We can also immobilize the cells, immobilize the enzymes, whatever we need actually. So here we are just talking towards immobilize the enzyme. So what is the importance? Why we are doing it? So that is the main question we also concern here. Okay. So the first thing is we can able to degrade, because enzymes are very sensitive. So it can able to deactivate. Also it can able to degrade. So that is the reason. That is a that is the main purpose of immobilizing any enzyme. You can take any cellulase, you can take lipase, you can take lactase, or any enzyme. So the main concern is to protect the enzyme from the degradation thing. So also we cannot lose the enzyme, because the enzymes can be recycled for many times. So we can use the enzymes for many number of times. Okay, so that is one of the reasons. Also the cost, as I told, like no, we have to lower the total cost of the thing. So because in the end of the application we have the life cycle assessment. So that is one of the main concern here. So the third one is like ability to stop the reaction. That is when it is actually when you are removing, or when you are actually doing a application part, we have to be careful in the reaction conditions. Okay, so then the fourth one is like stability. So we have to enhance the stability of the enzyme, so that it can able to do its own nature. Okay, so the stability is also one of the main concern here. Okay, so the fifth or sixth point is like no, we have to separate the enzyme. Once it is used, they can we can able to separate the enzyme from the product. So once the reaction conditions are over, we can able to separate the product. Okay, so then the last one is the product should not be contaminated with the enzyme. So that is also a concern here. So there are many reasons why we are going for a immobilized enzymes or immobilized biocatalyst here. Okay, so there are many advantages. Just a minute, just. So here there are some advantages in this immobilized enzyme. So here I have given you the list of advantages, like we can reuse, like versatility, so cost effective. So there are many advantages over here, like easy recovery, or like no easy purification. So in with respect to enzyme, so there are many advantages here. So we can able to store, we can able to reduce the enzyme inhibition with respect to anything. So better control over the reaction. So higher enzyme loading. So enzyme loading. So that is when the enzymes are like loaded in the immobilized part. So that is in the nano immobilized part, we can have a better yield or better product actually. So there is one more concept here. And also we have a co-immobilization. Okay, so when you immobilize it or like no, when you have a multiple enzymes, or like we have a pool of enzymes, so that also we can able to do it. So we have a co-immobilization of the multiple enzymes that facilitates the easy process of the things. Okay, so when we have lot of advantages, also we have a challenges here. So what are the challenges when you go for a nano immobilization? Okay, so we have the first thing is like normally we should not lose the catalytic property. So that is the main challenge here. So when you lose the catalytic activity, so then there is no meaning you do the nano immobilization. Okay, so loss we should carefully see the catalytic activity in the nano immobilized part. So then we have a mass transfer limitations, like we have internal, we have external mass transfer limitations. So that also we have to see in the challenging part. So these are the things which we should, when you design any immobilized catalyst, so you should see the challenges, or we should encounter, or how to overcome these challenges. Okay. So then we have the inhibition, that is the substrate inhibition will be a major concern. So what substrate you are going to use, whether it is inhibited or not, that also we have to see in the thing. So then the fourth and fifth point is like we have to see what is the enzyme carrier, what is the cost of enzyme carrier we are going to use, what are the things which you are going to use. So the cost mainly we have to see at the end. Okay. So then we have the degradation part. So whether the enzyme carrier or enzyme support is able to degrade or not. So if it is degraded, then we cannot use it. Okay. So then we are going with the industrial scale. So the limitations should be there. So whether it can able to scale up or not. So we have challenges over there in the nano immobilization or nano immobilized by catalyst. So generally, like before going into the research part, so there are some support materials. Okay, so we have organic, inorganic nanomaterials and hybrid nanomaterials. Okay, so initially we all studied only about the chitosan, alginate, then like normal polymers like cellulose, agar-agar, keratin. So these are all the normal natural polymers which are all like which are all available in the market. So just a minute. So yeah, so next we have a subdivision in the organic. We have a synthetic part. So we have like polyurethane, we have like polyethylene, polypropylene. So we can also use a synthetic organic one. So normally in the lab and all in the colleges we use like chitosan, alginate, all those things. Okay. So nowadays we have like inorganic material, like we have titanium, zirconium, gold, silver. These are all normally we have explored many of the researches. Okay. So now we are also going into the nanomaterials like titanium nanoparticles, metal oxide, nano-sized chitosan nanomaterials. So this also having these are all also playing a support materials. So then in the last, you can able to see the hybrid nanomaterials. Okay, so where we have like able to combine silver nanoparticles with water soluble polymers, or like we can take a magnetic gold nanoparticles with iron oxide. So we have a hybrid, that means a composite. We can able to do multiple composites over here. Okay. So nowadays there are a lot of support materials are available. So we have to see which support material will be suitable for our work, and then we have to choose accordingly. So we cannot be able to do it blindly. So we have to see what is the criteria behind that. Okay. So before going again to enter into the research, so we have to see the science behind the immobilization, like the basic of like what are the mechanism involved, or how it actually immobilize it. So what are the strategies we can able to do it. Okay. So to achieve a high stable like heterogeneous biocatalyst, we have some two main strategies are involved here. So one is like naturally stable enzymes. For example, we can take some estimophiles, or like we can also take some psychrophiles. So whatever we have a different kind of biocatalyst which is available, we can able to do with that one. Or also we can able to do a highly stable engineered enzymes. That means we can able to clone, or we can able to CRISPR-Cas, or like we can able to engineer the enzymes, and we can able to get a stable one. Okay. So if it is an unstable one, so we can able to do a like stabilization strategies, like with the different rational immobilizations. That is the second strategy we always go with. Okay. So here if you see what are the improvement in the three-dimensional stability of enzymes. Okay. So we can able to go with them. For example, when you have a multi-point attachment. Okay. So we have like lot of agents, like we have heat, organic solvents, or like extreme pH values. So these are all the things which can able to actually distort them immobilized part. So we have to see that. So once we are able to overcome this one, we can able to get a stable enzymes in the research part actually. Okay. So And the science, again, the many of you nowadays, the students are actually not concerning about the science behind this enzyme immobilization. So blindly they are doing, they're taking the enzyme and then they're immobilizing it, and then they are taking the application part. But we have to see how much the stable, what are the stability of enzymes. Okay, so when we are formally when you immobilize inside your porous support, okay, for example, you take a porous support. So what are the mass transfer limitations happening? So how to overcome that mass transfer limitations or any other aggregation happening inside the immobilized enzyme? So that part we have to be very careful and we have to choose that one. So that enzyme stability or the science behind that we have to see. So also when we are going with a multi-point immobilization, for example, we have a highly activated support which can promote which can promote the different enzyme orientations. So you can see if the support in the during the support, so there are many orientations which can able to affect it. So that physiochemical multi interaction between the enzyme and support surfaces should be taken into account. So hello, getting a echo here.
It's audible, sir.
Yeah, but there is some echo is coming actually. Yes. No, it's okay. So if you see this multi-point covalent immobilization, just for an example here, with reactive lysines. Okay, so the black color is the actually support, and this is just we have the enzyme where we have like between the lysine residues of enzymes. So if you see when you go with the harsh conditions like pH 10 or pH 11 with the reactive lysines, so we have a 2-point attachment. If you see in the attachment port, in the carrier port actually, so immobilizing the simultaneous 2-point attachment through the region with the highest density of this lysine rich region. So when we have more of like lysine rich region where we can able to attach it actually. So there are even we can also go with a covalent attachment with the very intense multi-point attachment also possible in the conditions. Okay, so so this is one of the strategies or one of the things which we also see the science behind or the mechanism behind the enzymes. Okay, so when you go with the preparation of highly loaded immobilized enzymes, okay, so we have to see the size of enzyme or size of the biocatalyst. So whether it is a small enzyme or a large enzyme. Okay, so accordingly you have to choose the pore size, whether you are polymer or whether you are chitosan or whether you are graphene oxide or whatever may be. So what is the pore size you are going to choose? Okay, so if it is small enzyme, small pore size, or if it is a large enzyme, large pore size is definitely needed. Okay, so when we are going with a small enzyme and small pore size, so obviously we'll be getting a high surface area which is much needed, where we can load more amount of enzymes. Whereas if you go with large enzymes, so we'll be getting only low surface area, and obviously you can load only low enzymes. So this point, or this is the concept we should always note down, and we should see during the research what are the size of the enzyme and how it can be choose, or how we have to choose the nanomaterials. Okay, so here if you see the global enzyme production, okay, so in 2014 if you see it is around $4.6 billion US dollar, and in 2022 or 23 you can see there is a $10.2 billion. So that means it is not only doubling, actually it is actually going for in the just 8 years or 9 years down the line. So it is actually the want, the global enzyme production wanted is that much higher actually. Okay, so we can take generally enzymes, so or a biocatalyst. Okay, so where we can able to immobilize the enzyme. So with respect to many industrial applications, we have textile, we have detergent, wastewater treatment, environmental, energy, Oh, so there are many applications or many more applications are there. We can able to combine also in the research. Okay, so with this background, we'll be slowly moving on to the research which we are actually doing it in our lab actually. Okay, so in our lab or what we do in my research, basically we are working from 2012 2013 onwards. We are working on this immobilization strategies with the different materials, with the different enzymes and all those things. So normally we do like encapsulation, we do cross-linking, also we do the simple adsorption, entrapment. So all this four different pods will do it actually, and accordingly we can able to choose the enzyme. So around that we can also have a lot of both organic, inorganic as well as the polymers. So with this combination we can able to choose uh, the materials. Okay, so the technology is given in the green color box. So that is the thing, and the outside is the material which we are actually working on. So where we are mostly concerned on the metal organic frameworks, also some composites, nano composites, metal oxide nanoparticles, and even silica or like porous silica nanoparticles. Also we are working, and magnetic nanoparticles, which is our the hot topic in the research. So and also carbon nanotubes. So all this graphene, all these things we are taking into account, and then we are keep on doing different strategies and different immobilization technologies. We are doing it, and then we are working in our lab actually. So this is one of the paper, like one of the research we already published in the year 2021 in the environmental chemistry letters with an impact of 15.5. So here we have given you the overall idea of the immobilization of the lacase with respect to the detection as well as the remediation of pollutants. So the two different pollutants, how to remediate the pollutant or how to detect the pollutant. So we have given you a overall idea of the immobilized enzyme, because lacase is one of the miracle enzyme. So where it can able to do lot of applications like so that again the lacase can be taken from different sources actually. So we are also working on this area, immobilization of lacase and application detection and this remediation of pollutants. Okay, so here in this paper, we have mainly focused on the biosensor development, and even the dye degradation. We have different dyes available, methylene blue, Congo red. So many dyes are available. So in the industrial effluent, so that we are doing it the dye degradation part, as well as degradation of phenolic compounds, as well as pesticide or herbicide degradation. So we have lot number of publications in this pesticide degradation with respect to lacase, as well as with respect to many nanocomposites. Also, we have lot of paper in the degradation. So now we are working on the biosensor development through the immobilized lacase. So once we immobilize the lacase, we can able to do the sensing part. So because many of you are not working on the biosensor region, so we can able to take the enzyme, lacase enzyme, and we can able to immobilize it in the graphene-based nanomaterials or metal organic frameworks. So when you talk about metal organic frameworks, so it is having both organic as well as inorganic property. So it is one of the hot topic where more number of enzymes are immobilized, and the applications can be developed, and you can still many research gaps are there in the MOF. Okay, so and also with MOF also we can able to go with the composites, MOF metal organic frameworks, and then polymers. So when you immobilize this functionalized MOF or functionalized nanomaterials, so we can able to give many applications. So here we have given you the biosensor application. Lot of receptors or lot of biochemical reactions can happen in this region, and we can able to get the signals here. Okay, so this is one of the thing which we are doing it in our lab also. So in this table, we have given in the research article itself. So we have taken the lacase from different sources, like right from the Novozymes, which is a standard enzyme. Right from that, we have a lot of things from archaea, we have from bacterial, we have fungal sources. So we have a lot of lacase sources. And if you see the support matrix, okay, so in the last 10 years itself, there are many research going on this, region, like right from calcium alginate beads, right from genipine, nylon fibers. So lot of support materials are there, and once you immobilize the enzyme with the support matrix, then we have to see the kinetic parameters. So how long the Km and Vmax. Okay, so what is the when with respect to free enzyme or with respect to immobilized enzyme, how this Km and Vmax is actually changing. So what is the kinetic constants, how they is behaving. So we are if we are very good engineering students, so we can able to work on this Km and Vmax, and you can able to see the immobilized kinetics part also. And from the starting, I told, like, no, stability of the enzyme, the two after the immobilized enzyme is very important criteria, because how many cycles or how many times we can able to recycle it. So that you can able to check, or you can able to modify it, or you can able to enhance that part. And application also, like, no, when you are going with a different interest, like, no, from biodegradation, some decolorization, or like, no, removal of phenolic compounds. So all this are the application. So application is like different, but how much your like biocatalyst is more stable here. So that is one of the important thing. So in last year, we also published an article, that is immobilization of cellulose enzyme with respect to nano and micro materials for the breakdown of cellulose in the for biofuel production. Okay, so here we talked about more on the cellulase enzyme. Okay, so we have taken cellulase. Now cellulase is also one of the hot topic in the biofuels, that is in the bioethanol. We have a lot of enzymes available, both in the commercial as well as in the fungal source, as well as from the streptomyces, as well as in the bacterial also. So again, we can see there are a lot of support materials, which I told in the earlier, like, we have Fe3O4 chitosan nanoparticles, and activated carbon, like graphene nanosupports, multi-volt carbon nanotubes. There are many research going on in this support itself, and like amount of enzyme immobilized, like, the loading capacity. So if the loading capacity is below 50 or something, then that means you are not chosen the right enzyme and right support material. So we have to see there. So how much you are going to load. So that is one of the important criteria. And how much of reusability. So when this both are above 60 or 70%, you are actually working in the right direction. And also, like, the application is mainly biofuel, like bioethanol, and sometimes you can also go with some targeted drug delivery, sometimes in the biomedical field, but mostly cellulose hydrolysis or bioethanol production is the only key area with respect to cellulase, actually. So we particularly taken only the metal organic framework, and we have given you the second table, where only with respect to MOF, how much of enzyme loading. If you see the previous table and this table, the enzyme loading capacity is actually higher, and also we can see the sustained the number of cycles we can able to recycle. That is also actually enhanced one. So this is the for the next generation, or next 5 to 6 years, this will be the metal organic framework will be the a major field where you can able to concentrate. So that is mainly I want to stress it here. And sorry, yeah. So this is the research article where my research scholar actually working in this nanocomposite, where we have immobilized the cellulase from the commercial cellulase. We have taken it, and then we have immobilized with the Fe3O4 GO and CS composite. Where in this work we are actually we can able to recycle the catalyst. Here we have done only in the batch. So now we are modifying it through for the continuous operation. And So here some of the results I will be sharing you. So how we have done it, we have taken Fe3O4 and initially we have prepared Fe3O4 and we also synthesized graphene oxide through modified hummus method, and we initially we combined Fe3O4 and graphene oxide using sonochemical dispersion method, and then we have taken the chitosan. So chitosan, we have three varieties are there, three different molecular weights. So we have to choose the right molecular weight according to our enzyme. So we have taken the chitosan and then we have made a composite. So this composite, we are now the composite is ready. So we have to check or we have to characterize the composite. So once the composite is characterized, so then we can able to immobilize the enzyme, cellulase enzyme through simple adsorption. So there are many techniques available, I told. So we have covalent simple adsorption, we have multi-point thing. So we have taken only a physical simple adsorption, and then we have taken our the biocatalyst is ready. So now we have done we have taken the lignocellulose biomass. Okay, so we have pre-treated it, and then we have added our this biocatalyst along with the cellulase enzyme. So now it is going to break this cellulose, hemicellulose, and lignin part. So once it is actually once it is the bonds are broken, so we can able to get the maximum amount of glucose. So this glucose can be we can able to ferment through some saccharification process. So we'll be getting the bioethanol. So even if you see the current trend or current news, which is last 1 month is going. So lot of from sugarcane bagas, they are actually the government is also allowing to go for the bioethanol, and in 2025 around 20 to 25% bioethanol is going to be blended with the petrol. So this is one of the key area where many companies are working, and this will be the future trend actually. Okay. So the results, okay, so we have made our lot of Fe3O cellulose composite, and if you see the last one, the eighth one is our work actually. If you see, they have done, we have not done any cross-linking, but we have just done only the simple adsorption, and the stability of the temperature with respect to temperature, it went to 80 degrees. And pH is around 8, and 4 times we can able to recycle it, and the biofuel yield is around 94% with respect to rice straw, and then this wheat straw. So we have taken two thing, and we have actually worked. So this comparatively, when you see other things, they have taken amylase, cellulase, lipase, and all, but here it is actually working well in the in our lab actually. So we are now going for the next level for the research. Okay, so this is the actual concept. So we have taken, now we are working on the different MOF in our lab. This is not published yet, but we have taken cellulase from the actinomycetes, and where this enzyme is a multi-enzyme. So that means it is having all the three enzymes. Okay, so with this, we'll be taking any magnetic MOF. There are many magnetic MOF, hundreds of MOFs are available. So we have in our lab more than 10 to 20 different MOFs we have synthesized, and we are going to check all the different MOFs with our cellulase multi-enzyme. Okay, so we are going with the cross-linking. We are going to change the surface, or we are going to engineering the surface morphology. So once we surface morphology is increased, more amount of enzyme can be loaded. So obviously more amount of glucose will be the final product. Okay, so obviously we'll be getting more amount of bioethanol. So that is the idea. So when we want the final product, so we want to change the surface area, the stability, all those things. So once we have done all those things, we can able to get the maximum thing. So also this is from another paper we have taken it. So there are many other modifications, nanobiocatalyst modifications they are doing it for improving in the biomass treatment, and other things like polysulfonic acid, the silver nanoparticles. So many things are there. They are coating it, and then they are getting many high ethanol production. So so many companies or many startups are going to come in this bioethanol region. So this is one of the key area or key thing which we are working in our lab. So this is another work which is recently published, just silica magnetic catalyst with for bioethanol production, like with different bio waste, but not by the pre-treatment by means of like other things like no ultrasonics and all. So here also we got a very good results. Okay, and in the down the line, maybe during my PhD work, I have done with the beta galactosidase, that is for the lactose hydrolysis and all. So we are working on this immobilization part with the different enzymes. So some are published, some are unpublished, and some have been patented. And we are keep on going with this immobilization strategies or immobilization, the different routes or different varieties of things we are able to do it, and also even some hydrogel concepts also coming in this immobilization part and all. So so this is with respect to the topic, like no immobilization, like no, when you see how this immobilization part with respect to nanomaterials. Okay, so when we are really work on this area, definitely you can able to achieve it, and you can be able to get some real time idea here. This one, so I think. Uh, this I gave you overall idea of about this biocatalyst as well as in bioenergy as well as in the with the different to any biotechnological applications. I have given an idea. So if you have any queries, or you can able to interact.
It's time for query sessions. Dear participants, is there any queries? You can also ask your questions in the chat box. Thank you so much, sir, for your informative presentation. We'll wind up the session.
Yeah, thank you. You can contact me if you have any doubts. You can write a mail to me.
Sir, there is a question in the chat box.
Yes. What's the question? Can you please read this question? Because a lot of comments are coming.
From Dr. K. Nagarajan.
So how do you, what is that? It's a spelling mistake or what? What is, how do you assess? Can you please read
How do
it?
you assess galactosidase enzymes?
Sorry, how do you?
How do you assess galactosidase enzyme?
Galactosidase enzyme, general enzyme, right? It's not about the immobilization.
Yes, sir.
How do you access, how do you characterize it? Like the enzyme part. Question is not clear actually. Which method will be more suitable to immobilize the hydrogel? So in hydrogel, if you are using it, we can go with you can take any composite, and then there is a separate protocol for a hydrogel. We can able to follow that one and do it. Normally, we take any composite and then like any polymer. Normally, a polymer should be there for making a hydrogel, because hydrogel is the next future topic actually. So you can take any chitosan or any polymer over available, and then you can able to do it, because hydrogel can be used in the batch as well as in the continuous process actually. So there is no particular definite method or definite protocol for them to make any of the things. So we can able to modify accordingly. Okay.
One basic question, why immobilization is done to reuse the enzyme further?
Because the enzyme is costly, obviously, so you cannot lose the enzyme.
Okay.
So if you want to lose the enzyme, so obviously the cost of the product will be going. So definitely you cannot lose the enzyme. So we can able to recycle it so that the productivity can be increased actually. So in the industrial sector or industrial point of view, definitely they look for the cost wise. So that is the reason we are going for the immobilization.
Okay, thank you.
How do you characterize the galactosidase enzyme? So enzyme characterization, if you ask, like there are many characterization. You can do SDS page, or you can able to do the protein or general characterization. If you ask, like there are many things are there. You can go for LCMS. You can do zymogram. What is the molecular weight? So all those things can be done to characterize the galactosidase enzyme. Any other questions?
Thank you so much, sir.
Thank you. Thank you. Shall I leave now?
Yeah, sir. Thank you.
Thank you.
On the